So going over these questions from your sample quiz. Question number one, you were asked the odds against an event are 5 to 9. You want to know what the probability that the event will fail. So whenever you're dealing with odds against, and that's the operative word here, it's odds against, you have your basically the number of failures first and the number of successes second. So the number of failures is 5, the number of successes or the number of instances where you succeed is 9. So, 5 parts fail to 9 parts succeed. That's 14 parts altogether. And since that's 14 parts altogether, the probabilities would be 5 out of 14 and 9 out of 14. So the probability of failing is 5 out of 14, which is approximately equal to 0.3571 when you round to 4 decimal places as directed. For question number two, you're told there are 8 candidates for 3 positions at a store. One position is for front cashier, the second position is for the menswear department, and the third position is for the sporting goods department. Candidates are equally qualified for the 3 positions, and how many different ways can the 3 positions be filled? So basically, you're being told that you have 8 candidates that they can take any one of these 3 positions. So it's basically, everyone has an equal chance of being selected for any one of these positions. However, the order does matter here, because if you look at an instance here, if say 3 people were chosen, John, Mary, and Kyle, and John's the cashier, Mary's working in sporting goods, and Kyle's working in menswear, that's different than saying that Mary's the cashier, Kyle's in sporting goods, and John is in menswear. I mean, the same 3 people are being hired, but these are different circumstances. So the order does matter, and because the order matters, we're dealing with a permutation rather than a combination. So we're going to be doing the permutation 8p3. Now the formula for this, of course, 8p3. This is the number of total candidates. This is the number being selected from that group of 8. So it's going to be 8 factorial over 8 minus 3 factorial. They usually say n factorial over n minus r, where n's the total number, r is the number being selected from that group. So it ends up being 8 factorial over 5 factorial, which is 336. So there's basically 336 different ways that these 3 positions could be filled from this pool of candidates. For question 3, an insurance company reported 60% of all automobile damage claims were made by people under the age of 25. If 8 automobile damage claims were selected at random, determine the probability that exactly 2 of them were made by someone under the age of 25. So we're just looking for exactly 2, not 2 or more, 2 or less, just 2 exactly. This is a binomial distribution because either they're going to be under 25 or they're not. I mean, so if 60% of the automobile damage claims are people under 25, that means 40% are not. So I'm looking for the probability that when we have 2 of them, or 8 automobile damage claims are selected, 2 of them are under 25. So the probability of having a driver in an accident that's under 25 is 60% or 0.6. Q is the probability of a failure. So if there's 60% success, 40% is failure. N is 8 because we're choosing 8 automobile claims, and we're looking to see, out of those 8, what's the probability of getting exactly 2. So P of X we're going to use this formula here, which is the combination of N of X times P to the X power times Q to the N minus X power. And we're just using these values here. So when I substitute those values in, I'm doing the combination of getting 2 out of 8 times 0.6 squared times 0.4 to the 6th power. And I work out the formula for the combination, although a lot of calculators can probably handle that. And you end up with 0.0413. So about a 4.13% chance. We're just looking for probability, so 0.0413 is what we're looking for an answer here. Question 4, a car rental agency has 11 midsize and 13 compact cars on its lot, from which 7 will be selected. Assuming that each car is equally likely to be selected and the cars are selected at random, determine the probability that the cars selected consist of 4 midsize cars and 3 compact cars. And we want to round that probability to 4 decimal places. So the probability of selecting 4 midsize and 3 compact, if we're basically selecting these at random, Um, well, my bottom number is going to be, well, we're selecting 7 cars out of 24 because there's 11 midsize and 13 compact. That's 24 in total. So the bottom number here of basically possible combinations of cars is a combination of choosing 7 out of a lot of 24. Now for the top numbers, we're going to go into their specialized categories. We have 11 mid-sized cars, and we're looking to see what the probability of getting 4 of those are. So I'm going to have the combination up here of 11 mid-sized cars, a combination of choosing 4 from those 11, times, since we have 13 compact cars and we want to see choosing 3 of them, I'm going to do the combination of choosing 3 from a total of 13. I multiply these two numbers together and divide it by this number down here. That's going to give me the probability of this instance occurring. I mean, it doesn't matter which order they're picked. I mean, if I go do the 4 mid-size and the 3 compact in that order, or if it's mid-size, compact, compact, mid-size, compact, mid-size, or something like that, combinations take care of that because the order doesn't matter. These numbers end up being 330, 286, and 346,104. When I multiply these together, I get 94,380 over 346,104. And that probably comes out to be about 0.2727 when you round to 4 decimal places. Question 5 has a partial figure there. We'll explain why that's there in a moment. But basically, you have this table here, and it's showing the 2 meals, lunch and dinner. How many said there was good service, how many said there was poor service, and of course the total number of people that were at that particular meal. And these are the grand totals down here. And there's a number of people who said they had good service, poor service, and a number of people that were involved in this survey. If one of these patrons is selected at random, find the probability that their service was poor, given that their meal was dinner. So basically what's going on here is you have this phrase, given that. Probably being poor, given that we're looking at dinner here. So given that we're that the meal was dinner, we're not taking the grand total here. We're not looking at all 2,423 people. We're only looking at those who were at dinner. So at dinner we have 1,567 who are at dinner. Now we want to see what's the probability of them saying that it was a poor service given that they were at dinner. Well, I can see here that there were 662 people that said they had poor service. And that's out of the 1,567. So I'm not going to take the probability out of 2,423 because the given that excludes those who were at lunch. We're looking at those who were at dinner. So that word given that is basically saying there's a condition being put here that you're probably not going to be looking at the entire sample as a whole. If they just said, what's the probability that someone said that they had poor service, I would look at this number here out of this number here. But given that it's dinner, I'm only looking at these numbers right here. And of course, that probably ends up being about 0.4225. Question number 6. A monk crossbred plants which have purple or white flowers and obtain 265 plants with white flowers, 239 plants with purple flowers. Find the empirical probability that a plant had each type of flower. So basically, we're looking for the probabilities that are based off of the numbers we actually had. So, we had 265 white flowers, 239 plants with purple flowers, so that gives us a grand total of 504 plants. So 504 plants we're looking at. So the probability of getting a plant with a white flower would be 265 out of 504. And probably getting a purple plant is 239 out of 504, which if you work these out and divide them and round to 3 decimal places, you get about 0.526 and 0.474 respectively. And these should add up to be 1 or 100% because those are the only 2 possibilities that we have, and they do. So sometimes you might be asked to find the probabilities, all the probabilities involved here. And you should know the probabilities. If there's only like 2 different things that can happen, well, the 2 probabilities you're finding should have to be a total of 100%, or 1 in this case. Alyssa and Gabriel play the following game. Alyssa rolls a die. If she rolls a 1, 2, or 3, Gabriel gives Alyssa $15. If she rolls a 4 or a 5, Gabriel gives Alyssa $10. However, if Alyssa rolls a 6, she gives Gabriel $50. So we want to figure out what Alyssa's expected winnings is and what Gabriel's expected winnings is. If this is a fair game, then basically both of their expected winnings should be 0. But if it favors one than the other, then one's going to, on average, get money, and the other one's going to, on average, lose money. So I'm going to set out here and describe what the rules and outcome and the probability are. So the rules, 1, 2, and 3, Alyssa wins $15. There's 3 different numbers out of the 6 that a die has, so that's 1/2 of the probability. So the probability of that happening is 1/2. Rolling a 4 or a 5, that's 2 out of 6. That's for a 1/3 probability, and that's when she gains $10. And of course, if a 6 is rolled, Gabriel wins 50. That's a 1 out of 6 chance. Now, even though he may have overall, a low probability, if this value is high enough, he can still end up being the one that's on top most of the time, provided the game is played more than once. I mean, if it's played only once, then chances are, she's going to probably get something out of it because she has more chances of winning than he does. So, expected winnings for Alyssa. So I have to look at these more specifically because I have both these according to what they both will win. I have to look at, when I look at Alyssa's expected winnings, I got to look at what her outcomes are only. So for Alyssa, she can gain 15, that's a 1/2 probability. She can gain 10, that's a 1/3 probability. Or she could lose 50, which is a 1/6 probability. So her expected winnings is basically just the average based off of this. And finding the average, or the mean, I'm just going to take each one of these x values and multiply it to its probability and then add them together. So 15 times 1/2 plus 10 times 1/3 plus negative 50 times 1/6. And if I work that out all together, I get $2.50 even. So on average, we expect Alyssa to win $2.50. Now, I could just use some logic here and just automatically assume, well, if Alyssa's going to win on average, Gabriel's going to lose on average, and he should lose $2.50. But, I worked out the longer way here too. Just his circumstance is a little different. I mean, each case, in the first 2 cases, he's losing money. So he has a 1/2 chance of losing 15, a 1/3 chance of losing 10, and a 1/6 chance of gaining 50. Of course, you multiply each one of these by their probabilities and add them together, you do get a negative $2.50. So, logic could probably dictate that, but it could also be calculated the same way we calculated Alyssa's expected winnings as well. Question 8. I already have part of it underlined. A cooler at a picnic contains 100 cans of soda covered by ice. There are 28 cans of cola, 27 cans of orange soda, 17 cans of ginger ale, and 28 cans of root beer. The cans are all the same size and shape. If one is selected at random from the cooler, determine the probability the soda selected is ginger ale or root beer. Well, first of all, it has to be an or statement because, I can't have ginger ale and root beer. I mean, I never heard that combination being, sold by anybody. Maybe it's good, I don't know. But it's either going to have ginger ale or root beer in it. And since it's a probability with an or statement, I'm going to basically take those 2 numbers for the top number. So it's out of 100, we have 100 cans. And I'm going to add those 2 together, 17 plus 28. Which is 45 out of 100, which is 9 out of 20, which comes out to be 0.45 exactly. So rounding it to 2 decimal places, you do get 0.45. So it's not a very difficult problem. You have to realize for an or statement, I have to make sure that, I'm taking each one of those into consideration. And these are mutually exclusive events. If I have ones that can overlap, I have to be really careful, especially when I start dealing with and situations and or situations, that I'm not counting some things twice or excluding something on accident or things of that nature. Question 9. When playing bingo, 100 balls are placed in a bin and balls are selected at random. Each ball is marked with a letter and number is indicated in the chart below. For example, there are balls marked B1, B2 up to B20, I21, I22, up to I40, and so on. And they're showing all these things here. So we have 100 different bingo balls, and one is selected at random. What are the odds in favor of it having a G on it? So basically, you know, there's 5 groups here. Each one has 20 balls in it. So there's 20 balls with G on it, which means that there's 80 that don't. And these are the numbers I'm looking for when I do odds. You know, I'm looking for those that fit a category, those that don't fit a category. It's usually like, you know, it has this or it doesn't have this. When it's odds in favor, that means I'm going to put the number of successes first, number of failures second. If it's at odds against, I'd put the failures first and this second. It's really the only difference between the two. So in this case, odds in favor is a 20 to 80 ratio. Now we always simplify this into lowest terms. You know, these are both obviously divisible by 10. It's a 2 to 8, but these are still both divisible by 2. It's a 1 to 4 ratio. And they always expect you to give it in lowest terms. Even if it doesn't ask for it, it's expected. So make sure that you are putting those in the lowest terms. Otherwise, you might get marked wrong on my MathLab quiz if you don't. Question 10. If the pointer in the figure is spun twice, find the probability that the pointer lands on green, then red. So basically here, it isn't like whenever we land on a color here, the color disappears. So this is going to be an instance where I have replacement. And that's important to note because, you know, when I have instances with replacement and instances without replacements, I had to make adjustments accordingly. So when I look at this wheel here, you know, it kind of shows here I have one half of it being red. This is the other half shared equally by green and yellow, so each one has a 1/4 probability. So we're looking for the probability that it lands on green and then red. That's a specific order. If it just said out of 2 spins, it lands on green once and red once, and it's not particularly that order, that's a slightly different circumstance you have to be aware of. But for this one here, it specifically says it lands on green and then red. So it's going to probably it lands on green first, then red second. Landing on green first is going to be a 1/4 probability. Landing on red second is going to be a 1/2 probability, because it doesn't matter if it's first or second. Landing on red is just going to be a 1/2 probability. So that's 1/8, which is 0.125 when rounded to 3 decimal places. Now, if they had said it lands on it's spun twice, that it lands on green once and red once, and not necessarily that order, then you have to find how many different ways you could have green and red together, which is only 2, so you'd have to double this. And say it's 1/4 of the time that you would have, you know, a green and red selected overall. So at the Royal Dragon Chinese restaurant, a slip in the fortune cookies indicates a dollar amount that will be subtracted from your total bill. Sometimes these underlines didn't get clicked the right way. Oh well. A bag of 10 fortune cookies is given to you from which you will select one. If 6 fortune cookies contain $1 off, 3 contain $2 off, and 1 contains $4 off, determine the expectation of a selection. So basically the selection, or the expectation, is an expected discount. You know, you're going to get a discount of some sort. On average, what is that discount going to be? How much is the Royal Dragon Chinese restaurant on average giving up with this selection process? So I am doing expected value again. So I'm going to need to figure out the different possible outcomes, which is the amount of the discount, and the probability for that. So the amount of discount, so we had 6 fortune cookies that contain $1 off. So the amount of discount is $1. 6 out of 10 of the fortune cookies are going to have that. So it's a 3/5 probability when you round it off. You can even just say 0.6 if you want to. I mean, for this one here, because the decimals do all tend to terminate, you could write them in decimal form. It's usually, I mean, that's okay too. Usually writing it in fractions is cautionary, because you may get some fractions that don't have a repeating pattern immediately, and you might want to round them off too soon in the calculation process. We have $2 off as another possible discount, and there's 3 of those balls that contain that. And of course the last one is a $4 off. The amount of discount is 4, there's 1 out of 10 on that. So as before, when I look for an expected amount or expected discount in this case, I'm going to take each one of these outcomes and multiply it to its probability and then add them together. So I'm going to have 1 times 3/5 plus 2 times 3/10 plus 4 times 1/10. And that comes out to be 1.6, or in this case, $1.60. So on average, the expected discount is going to be $1.60. this is an instance where you have to be aware of the fact that, the probability of A or B occurring can have, an instance where you have some that are both occurring at the same time. You don't want to count them twice. And we have a general formula for this. The probability of A or B equaling the probability of A plus the probability of B minus the probability of A and B. Now, of course, if they're mutually exclusive, this is 0 automatically. That means that if you drew a Venn diagram, you'd have two different circles with no overlapping region. A lot of times, though, if you have two different things that can go on and they're both independent of each other, then they should be able to both occur at the same time, as well. But using this formula here, I can easily solve this problem because I have 4 different variables in this formula. The variables are each one of these probabilities. And I know what 3 of them are. I know what this is, I know what this is, and I know what this is. I'm looking for this. So just putting those values in where they belong, simplifying the right-hand side, I get 0.60 equals 0.05 plus the probability of B. Subtracting 0.05 from both sides, I get 0.55 as the probability of B, which means that the probability of B is 0.55. So basically, that's the probability of that. So if you remember this formula, you can usually, if you have this information presented in this way, you can usually find any of these things, given that you know the other 3. So consider a collection of envelopes consisting of 3 red envelopes, 2 blue envelopes, 1 green envelope, and 1 yellow envelope. If 2 envelopes are selected at random with replacement, determine the probability that at least 1 envelope is a red envelope. So the probability that at least 1 envelope is red is. So now we could do this a couple different ways. I mean, I could realize that the way they're stating this, since we're looking at the probability of both being red, the only color we're really concerned with is red. So we can actually make this red and not red. So we have 3 red, and we have 4 that are not red. So you could kind of go that way and use binomial calculations and do the probability of, 1 red and the probability of 2 reds and add them together. That's a little bit more involved. It's not very long, but it's a little bit more involved than the option I'm going to show, because we have 2 envelopes selected at random with replacement. That's important. With replacement means that, if we pick a red envelope, we put it back, and there's still going to be 3 red envelopes when I make my next pick. That's important as I go along with this. But the other thing I'm going to do here to make my calculation a little shorter is realize that the probability of at least 1 red is the exact opposite of the probability that none were red. And so if I do 1 minus the probability that none were red, that makes this calculation a bit easier, because it's really easy to determine, okay, well, to have at least 1 red means I had to do 2 different probabilities. It was even something different that if I was picking 4 times, at least 1 was red, then I had to say, okay, well, I had to do probably 1, 2, 3, and 4, and do all those and add them together. It gets to be more complicated as you get the higher number of envelopes being selected, or whatever the case may be. So, anytime you're dealing with at least 1, know that none is the exact opposite. So the probability that none were red is going to be the probability the first one's not red and the second one's not red. So the probability the first one's not red is going to be 4 out of 7. Since I'm putting it back on the second choice, probably the second one's not red is also a 4 out of 7. So I'm going to have 1 minus 16/49, which is 33 over 49, which is 0.6735. And that brings me to the end of this video. If you have any further questions, please make sure to reach out and contact me. Until next time, have a good day.